All right, good morning, everybody. Welcome back to Path 2. Plan for today. A lot of discussion going on during my morning announcements.
Attention on deck.
Attention on that. Plan for today, we're going to have that promised quiz on Standard 11. Talk just a little bit more about the divergence tests, which we talked a little bit about yesterday, but I have a little bit more I'd like to say about it. And then jump into Standard 12, where we're going to be revisiting everyone's old friend, integrals. For one standard. Don't worry, they're not going to be around the rest of the semester necessarily. I've got my usual office hours today at 11 and at 1, as well as tomorrow at 1 o'clock. As far as homework goes, I posted some new web work this morning that'll be due Friday a week from now. Don't forget you have a homework due this Friday, as well as an exam next Friday on standards 1 through 12. Dr. Erskine, why are you assigning the homework today that's not due for like over a week? Well, that is because, as a reminder, we have no class this Friday and no class on Monday. So enjoy a little bit of enjoy your Easter break. Hope you hope it's a good Easter. Trying to look for like a good impactful word, and it didn't come to me. Have an impactful Easter break. Any questions or comments before we get started for today? All right. I need a volunteer for the joke of the day. Jonah has volunteered himself. All right. So Jonah, in this hypothetical world, is now a cannibal. And he is going to the local butcher shop to buy brains for dinner one night. So he goes to the butcher shop, asks for, some nourishment, where he is told that mathematician brain costs $1 a pound, engineer brain costs $2 a pound, and politician brain costs $10 a pound. Cannibals bewildered by this. Ask the butcher, wait, why does politician brain cost 10 times as much as mathematician brain? Is the quality that much better? Butcher laughs before replying, no, of course not. It just takes 10 times as many politicians to make that pound of brain. Oh. Ooh, political joke. Alrighty, and with that, we go ahead and pass out today's quiz. And as per usual, you all got this. go ahead and take a few seconds to finish up your thoughts. And with that, pass your quizzes in, please. Alright, so with that, I'm going to jump back into the end of Standard 11. If you recall, class on Monday, we spent a while talking about geometric series for most of class, like what was showing up on the quiz there. But towards the end of class, I also introduced a new theorem that I want to talk a little bit more about today, that being the divergence test. Where what the divergence test says, make sure I write this down correctly, is that if we have a series such that the limit as n goes to infinity of a sub n is anything other than 0, and we're trying to sum up a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, etc., then the sum of all your a sub n's must diverge. Or in other words, sort of intuitively, another way to think about it, if you have a convergent series, then the individual terms that you're adding up in the series have to go to 0 as n goes to infinity. So that it's impossible to have a series where we're adding up a bunch of terms that are not getting smaller and smaller and smaller in magnitude and expect to have that series come out to some finite number somewhere. So let's take a quick look at what that means in practice. So I'm going to skip ahead to the next page for just a second. We'll come back to kind of my last comment on that. Let's take a look at sum from n equals 5 to infinity of 4n squared minus 9 over 3n squared. So Joy, question for you. Is this a geometric series? Meaning, can this series be written as just being constant times some number r raised to the nth power?
You're going to have to separate it, I think, and we don't have to.
Ah, okay. So what you propose is that we split this up into two separate fractions? Okay? So if we do that, we'll get 4n squared over 3n squared minus 9 over 3n squared. And how would you handle each, what would you do with each of these pieces?
You would plug in 5 or n for 5 for the constant.
Yeah.
The constant of the second one would be 9 or negative 9.
Let's say, I think we have a little bit of an issue in that we don't have something raised to the nth power like we normally would in a geometric series. We have like we have a bunch of n squared terms that show up, but we're not raising something to the nth power. So I don't think this is going to be a geometric series, meaning we can't use our sort of test from yesterday, is the ratio r between -1 and 1 on this series, because there is no sort of ratio r that we can find here. So let's look at this individual expression though. This 4n squared minus 9 over 3n squared. I'm going to erase this for just a second. If we look at the individual terms that we're adding up, meaning if we take a limit as n goes to infinity of 4n squared minus 9 over 3n squared, how would we evaluate this limit? For right now, we're not looking at the series, we're just looking at the individual terms in the series. Well, there's a couple ways. We could just try plugging in big numbers for n and see if we notice any sort of pattern. James?
I'd actually should guess the first step we did for trying to evaluate the summation where you break it up.
Ah, so here's where kind of breaking it up, like what Joy was doing into two separate expressions, would be helpful.
Mm-hmm.
Sounds good to me. Okay, so we could write that as 4n squared over 3n squared minus 9 over 3n squared.
So then the n squareds cancel out, so then you can just ignore the 4/3.
Ah, okay, swoosh swoosh. And get a limit as n goes to infinity of 4/3 minus 9 over 3n squared.
Yeah.
Okay. Caleb, as n goes to infinity, what's going to happen to 9 over 3n squared? What's that expression going to go
Get
to?
really close to 0.
Yeah, because 3n squared is going to go off to infinity, and 9 over really, 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 really big number going to get really, 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 really small numbers. Anna, as n goes to infinity, what's 4/3 going to do?
Stay the same.
4/3 is going to sit down on its butt and not do anything, because it's not affected by what n is doing, since there's no n's in that expression anymore. So the whole thing is going to come out to 4/3 minus 0, or 4/3. So what does that mean? Well, if we're looking at the individual terms that we're adding up, the 4n squared minus 9 over 3n squared, we're saying that as n goes to infinity, the individual terms that we're adding up are going to 4/3. So what does that tell us about the original series? If we're adding up a bunch of terms that as n goes to infinity approach 4/3, what does that tell us about the original series? Is it going to be convergent or divergent, Bethany?
It's going to diverge because it's not going to 0.
Yeah. Because the divergence test says if this limit that we got was anything other than 0, the series would automatically have to diverge. So the series, sum from n equals 5 to infinity. This n equals 1, by the way, in the theorem, that's not super. That number doesn't have to be 1. That could be any number, really, that where it starts, as long as the individual terms are defined. So for this one, for instance, we wouldn't want to start at n equals 0 because then we'd have sad times dividing by 0. But I would say the series, sum from n equals 5 to infinity of 4n squared minus 9 over 3n squared is going to diverge because the individual terms don't go to 0. Because if you think about it, if you're trying to add up sum from n equals 5 to infinity, 4n squared minus 9 over 3n squared, as n gets bigger and bigger and bigger, eventually what you're going to be adding up is something that's very, very close to 4/3 over and over. And Katie, if we were to add 4/3 to itself over and over and over, take 4/3 plus 4/3 plus 4/3 plus 4/3 plus 4/3 and so on, would you expect that sum to come out to a finite number or to go off towards infinity?
Go off towards infinity.
Yeah, I would expect that to go off towards infinity. And in essence, what the divergence test tells us is that if the individual terms that you're adding up approach something that's not 0, like 4/3 in this case, there's no way for that series to converge. Because if the terms you're adding up approach 4/3, then you're essentially adding 4/3 to itself over and over eventually. If the terms we were adding up approach the limit of, say, I don't know, pi, then what you'd be essentially doing is you'd be adding pi to itself over and over and over again. And while your belly might approve of that, that doesn't make for a very convergent series. Pi. Any questions or comments related to this? Let's look at another example. Let's look at sum from j equals 3 to infinity of 2 minus e to the j power. So in essence, what we're going to be adding up is something like 2 minus e cubed plus 2 minus e to the 4th plus 2 minus e to the 5th, etc., going on forever. Watch it, you. Going on forever. If we were to take a limit, though, as j goes to infinity of 2 minus e to the j power, Allie, what would you expect that limit to come out to? As j gets bigger and bigger and bigger, what's going to happen to 2 minus e to the j power?
Well, the e term will keep getting bigger, so it would be negative infinity.
Yeah, we're going to get a limit of negative infinity. We'd have that e to the j power is going to go off towards positive infinity as j goes to infinity. And then 2 minus something going to positive infinity is going to be going to negative infinity. Jonah.
Sorry, it's a random question. If you did j like plus negative e to the j, wouldn't that change it up? But that's basically the same thing.
If you had what now?
It's you would do 2 plus negative e to the j.
Like that?
Yeah. Is
Yeah.
it the same?
Yeah, that's the same thing.
Right. So if you would take, j to infinity, that would be going. Wouldn't that be alternating between positive and negative numbers?
So when we say negative e to the j, do you mean e to the power of negative j?
No. I just mean like negative e squared is a positive number, but negative e cubed is not.
I see. I think what you're confusing, Jonah, is when we say something like negative e squared, that's what that means is you're taking e squared and then taking the
Okay.
negative of that.
Okay.
Which is not the same thing as taking negative e quantity
Okay.
squared.
Yep. There we go.
Yeah, if we wanted something like that, we would have to say 2 plus negative e raised to the power of j, which would give us a different expression.
Yep, thank you.
Yeah, good question though. Ba-ba-boo-ba-doo-boo. Bethany?
Say e were like, say e were like a fraction, like say if it were like less than, it was in between the -1 and 1.
Mhm.
Would that mean that, it would converge to 2, because technically the e keeps getting smaller and smaller, so.
The sequence would confuse to 2, yes. Or the individual terms we were adding. Actually, that's a good example. We'll talk about that in a sec after we finish this one up. Emerson. How you doing, Emerson?
I'm okay. How are you?
Doing good. Oh, you had a look of dismay when I said your name, so I figured I should check in. If the individual terms that we're adding up are going to negative infinity, meaning if we're trying to plug in values for j, what we're essentially doing is eventually we're going to be plugging in like negative infinity plus negative infinity plus negative infinity plus negative infinity over and over again. Is that going to give us something that converges?
No.
Yeah, I would agree. Negative infinity, I don't know what negative infinity is, but it's certainly not the same thing as 0. So we can say by the divergence test, the sum from j equals 3 to infinity of 2 minus e to the j is going to have to diverge. According to the divergence test. The individual terms we're adding up are not going to 0, therefore the series has to be divergent. So Bethany, you actually brought up an interesting question. What would happen if we replaced e there with like some fraction between -1 and 1? So let's take a look at that. What would happen if we wanted to take a sum from, let's say, I don't know, k equals 1 to infinity of 2 minus, let's say, 1/3 to the k power. So Bethany, what would you expect the limit as k goes to infinity of the individual terms be in this case?
They get closer to 2 as.
Yeah, 1/3 to the k is going to go to 0 as k goes to infinity, because if you keep multiplying the third by itself over and over and over, it's just going to keep getting smaller and smaller. So 2 minus something going to 0 is going to approach 2, I would say. And Sarah, if the individual terms that we're adding up are approaching 2, meaning this series eventually just becomes like adding 2 to itself over and over and over again, what would we expect the series to do?
It would go on for infinity.
Yeah, it would go on towards infinity, so it would
Diverge.
be divergent. Yeah. Since the individual terms, once again, are going to something other than 0, the series is going to have to diverge. And thus, by the divergence test, sum from k equals 1 to infinity of 2 minus 1/3 to the k diverges. So to kind of answer your question from earlier, Bethany, if we had changed that e to the j to something like a third, to some fraction between -1 and 1 to the j, the series would actually still diverge either way because of this 2 term. However, changing the e to the j versus something like 1/3 to something like 1/3 to the j, or 1/3 to the k, I don't know why I changed the variable name, but here we are. That determines whether or not the sequence of individual terms converges or diverges. But in either case, whether the sequence of individual terms blows up towards negative infinity or converges to some number like 2 other than 0, both of those would be indications that the series, the sum of all of these terms, is going to be a divergent infinite sum. Does that sort of answer your question? That's a good one. Any other questions, comments, or concerns? Let's look at one more example. This one's not in the packet, but it is one that I think would be interesting to talk about. Let's take a sum from n equals 1 to infinity of 1 over square root of n. So that would be like adding up 1 over square root of 1 plus 1 over square root of 2 plus 1 over square root of 3, etc., etc. If we were to take a limit as n goes to infinity of the individual terms in our series that we're adding up, Devin, what would you say you would expect that limit to come out to? As n gets bigger and bigger, what's going to happen to 1 over square root of n?
Oh, it's all going to go to 0.
Yeah. Square root of n is going to go towards infinity, and 1 divided by something going to infinity is going to go to 0. So with that in mind, you would expect then, hey, the individual terms we are adding up are going to go to 0. So James, you would expect that the series then would do what?
Probably convert.
Probably convert. And yet, if you notice, if you were to take this sum and take limit as n goes to infinity of the nth partial sum of this series, meaning we take a limit as n goes to infinity of 1 over square root of 1 plus 1 over square root of 2 plus 1 over square root of 3 up through 1 over square root of n. If you notice, Rhoda, let's say we know that 2 is less than n. 2 is a smaller number than n. Which of these numbers is going to be bigger than n? 1 over square root of 2 or 1 over square root of n?
1 over square root of 2.
Yeah. The one that has the smaller denominator is going to be a bigger fraction as a whole, right? Mary, let's say if we know that 7 is less than n. Which of those would you expect to be bigger?
1 over 7.
The 1 over square root of 7?
Yes.
Yeah, basically the same logic, right? Smaller denominator means bigger fraction as a whole. So if you notice, and we're taking 1 over square root of 1 plus 1 over square root of 2 plus 1 over square root of 3 up through 1 over square root of n, if we wanted to compare that to 1 over square root of n plus 1 over square root of n plus 1 over square root of n plus 1 over square root of n, which of these sums, Ty, would you expect to be bigger? The first sum or the second sum?
Bigger, probably the first one, right?
Yeah, because assuming 1 is less than n, this expression is going to be less than 1 over square root of n. 1 over square root of 2, plus sorry, this is going to be bigger than 1 over square root of n. 1 over square root of 2 is going to be bigger than 1 over square root of n. 1 over square root of 3 is going to be bigger than square root of n. So the limit as n goes to infinity of this expression, we would expect to be greater than the limit as n goes to infinity of this expression. Where here we have n copies of 1 over square root of n that we're adding together. So if we're adding together n copies of the same number, say 1 over square root of n. Christopher, let's say I had the number 3, and I wanted to add together n copies of the number 3. What would you expect that sum to come out to if you added 3 to itself n times like this? Well, n here is just some finite number. Let me rephrase. What would you get if you took 6 copies of 3 and added them together?
18.
10 copies of 3 added together. 1,000 copies of 3 added together.
3,000.
N copies of 3 added together.
3n.
Yeah, it's going to come out to 3n, right? And then if you were taking a limit as n goes to infinity of that, then that sum would certainly go to infinity. All right? Kate, let's say you've had n copies of the expression 1 over pi. And you're adding n copies of that together. What would you expect to get?
N over pi.
Yeah, you would expect to get n times 1 over pi, or n over pi, right? When you're adding n copies of something to get of the same number together, you're always just going to get n times that number. So with that in mind, Reagan, if we wanted to add together n copies of 1 over square root of n, what would we expect to get?
We get n 1 over square root.
N times 1 over square root of n, you said? Yeah, exactly. Since this is the same number every time, adding n copies of the same number is just going to give you n times that number. Or putting it the way Kate put it, that would give us n over square root of n. Phoebe, how would you evaluate limit as n goes to infinity of n over square root of n? If you want your answer, it can always just be try plugging in numbers for n and see if you notice a pattern.
Yeah, I would do that.
Okay, so that would give us like 1 over square root of 1 is 1, 2 over square root of 2 is square root of 2, 3 over square root of 3 is square root of 3, 4 over square root of 4 is square root of 4. Let's put it a slightly different way. If we had n to the first power over n to the 1/2 power, is there a way that we could simplify this at all? John?
Then you supply it to just n to the 1/2.
Yeah, that's going to be the same as taking a limit as n goes to n goes to infinity of n to the 1/2 power, or square root of n if you prefer. And Lauren, as n goes to infinity, what's going to happen to square root of n? As n gets bigger and bigger and bigger and bigger, what's going to happen to the square root of some number that's shooting off towards infinity? I don't think it's going to get smaller. I think it's going to keep getting bigger and bigger, and thus itself go to infinity. Alright, James, let me ask you this. If we go back to our original series for a second, or the original partial sums of the series, let's say.
Mhm.
The original partial sums, if you take a limit as n goes to infinity, that's going to be greater than than a limit that's going to infinity. What does that tell us about our original limit as n goes to infinity of s sub n?
So by the comparison test, it says that must also shoot off to infinity.
Whoa, comparison test. We have no such thing for series yet. But you're absolutely right. Yeah. So what does that tell us about the original series?
That must also go off to infinity.
And thus is going to,
Diverge.
yeah. So this actually tells us that the original sum, limit as n goes to infinity of s sub n, well, that's going to be infinity, which in turn tells us that the original series that we're looking at, sum from 1 to infinity of 1 over square root of n, is going to diverge. Even though the individual terms that we're adding up, 1 over square root of n, goes to 0. Well, that's weird. Doesn't the divergence test say that, doesn't the divergence test tell us that if the individual terms are going to 0, then the series has to converge? Turns out the answer is no. The divergence test says if the individual terms don't go to 0, then the series has to diverge. But it doesn't say anything about if the individual terms you're adding up do go to 0. It doesn't say that the series necessarily has to converge. Even if the limit as n goes to infinity of the a sub n is 0, the series could still either converge or diverge. And that's kind of why I wanted to go through this example to provide a moral, where the moral of the story is if limit as n goes to infinity of a sub n is non-zero, the sum of all the a sub n must diverge. But if the limit as n goes to infinity of a sub n is 0, the sum from 1 to infinity of a sub n may converge or diverge. Basically, the divergence test just doesn't tell us anything in this second case. It's kind of weird. You're adding up terms that are getting closer and closer and closer to 0 as n goes to infinity, and yet the sequence of nth partial sums is still a divergent sequence. Meaning the series is still going to can still shoot off towards infinity potentially, like what happened in this case. We had a nice happy result that the individual terms were going to 0, and yet we were still sad in the end because the series happened to diverge rather than converge. Joy, does that make you sad?
No.
It makes you happy?
Your little sad face makes me happy.
Joy, I'm glad you take such pleasure in my sadness. I guess that's why they call you Joy, huh? Happy no matter, happy whether others are happy or miserable. Okay, I'm sorry. I don't want to. Not actually. I'm just making that joke. Any questions or comments about the divergence test and what it says? Yeah, Aiden?
I have a question about how we're comparing n over n to the square root of n.
Mhm.
Isn't n over the square root of n larger than 1 over the square root of n?
This is true.
Then thus the conversion test doesn't work because the n over the square root of n is larger than 1 1 over the square root of n, so when we still can't say 1 over the square root of n is divergent.
Sure. N over square root of n. So we did that. As a sequence, you're absolutely right. But what we keep in mind though that this n over square root of n, what we're comparing that to isn't the sequence 1 over square root of n. It's the sum from n equals 1 to n, I guess, of 1 over square root of n. So the comparison test doesn't quite. If you wanted to use it on, if you wanted to compare the two sequences, you could say, sure, the fact that n over square root of n goes to infinity doesn't mean 1 over square root of n has to go to infinity. And in fact, as we kind of showed over on the left-hand side, that goes to 0. But we're not comparing this to that exactly. What we're doing is we're comparing n over square root of n to sorry, not 1 over square root of n. 1 over square root of 1 plus 1 over square root of 2 to 1 over square root of n. And this expression is actually going to be less than that expression. So the fact that this is going to infinity means that this, the nth partial sum, has to be going to infinity as well. Does that sort of make sense?
I think so, yeah.
Yeah. You're sort of comparing apples and oranges, in other words. Whether you're comparing the sequence to the sequence or the sequence to the series. Okay?
So is this case similar to when we were doing p integrals, where 1 over p to the third converge, or 1 over p diverge? But
I
it's still approach.
Would say that's extremely similar to that. In ways that we're going to be talking about momentarily, so I'm not going to say any more. Good question. Any other questions or comments about divergence test here? So if the individual terms you're adding up are not going to 0, series has to diverge. If the individual terms you're adding up do go to 0, series could converge or could converge or could diverge. And with that, that's it for standard 11. Let's move on to standard 12, where Dave has an interesting hypothesis that, hey, we said something about the integral from 1 to infinity of like 1 over p to the n. What does that tell us about the sum from n equals 1 to infinity of 1 over p to the n? Turns out there's a connection there. Because it turns out, Gabe, to actually answer your question, turns out the integral and the series are extremely related to each other. Because you can determine whether or not the series converges or diverges by whether the corresponding integral is going to converge or diverge, it turns out. Let's take a look-see. Boop, beep, that, boop. Where's my chalk? So this is a theorem that's called the integral test. So I've got all sorts of papers up here to fiddle around with. So it's going to be a test that we can use to determine whether or not an integral happens to converge or diverge. And what it says is suppose that f of x is a positive, decreasing continuous function of x on the interval from capital N to infinity. So in other words, suppose we're looking at a function that does something like this. That it keeps getting small, that it's greater than 0, it's a continuous function, and it's getting smaller as x gets bigger and bigger and bigger. So what we're going to do is we're going to let a sub n be the sequence defined by letting a sub n be equal to f of n for each n. So for instance, if we had this function here, f of x, and we looked at each integer, 1, 2, 3, 4, 5, etc., what we would do is we would define a sequence by saying the height of this point is going to be a1. The height of this point is going to be a2. The height of this point is going to be a3, and so on and so forth. And with that in mind, it turns out that the sum from n equals, say, some big M to infinity of a sub little n is going to converge if and only if the integral from n to infinity of f of x converges. So in other words, this kind of is going to help us tie together a couple of our definitions of convergence that we've seen throughout the semester, in that we can determine whether or not a series converges by instead looking at a particular improper integral and asking ourselves, does that improper integral converge? Because it turns out if the improper integral converges, then the corresponding series is going to have to converge. And if the corresponding improper integral diverges, then that series will also have to diverge. Let's look at an example where we put that into practice. Because this is a little bit of an abstract theorem that's not as hard to use, I think, as what it might initially look like. So let's say we were taking the sum from n equals 1 to infinity of 1 over n squared. This one's not in the packet, so maybe just put this on the first page of the packet if you're writing this down. So that would be like 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, etc., going on forever. Nathan, is that a geometric series? Meaning, is it a series where we're basically taking some constant to the nth power? No, it's actually like we're taking n to some constant power, not some constant to the nth power. So it's not geometric. We can't do our sort of test from standard 11 on it. So what we're going to do instead is we're going to convert this to an integral from 1 to infinity. And we're going to look at the integral from 1 to infinity of 1 over x squared, as opposed to the sum from n equals 1 to infinity of 1 over n squared. All right, Gabe, you're the one who asked this question earlier, so I'll put this to you. What do we know about this integral? It's a p integral, where p is 2, right?
Yeah.
So what does that tell us about the integral?
I believe it should converge.
Yeah, exactly. We know that this integral converges as a p integral with equals 2, which is greater than 1. And thus, by the integral test, we can say that since the integral from 1 to infinity of 1 over x squared converges, the sum from 1 to infinity of 1 over n squared must also converge. So in other words, knowing that the corresponding integral, where we basically change our n's to x's, knowing that gives us a convergent improper integral is enough to tell us that the corresponding series, where we're changing our x's to n's, essentially, has to be a convergent series. If you ask me, it's really cool. It kind of ties together two of our ideas. You all might disagree because it means we're going to be evaluating improper integrals in the standard, and some of you, I'm guessing, would rather not have to do that ever again. Well, tough luck, Devin, because you're going to have to do some in standard 12.
I want to take my phone to home.
So standard 6 is where we did our improper integrals, just as a reminder. Question. James, do you know what that series converges to?
No.
As I say, this is something where if you haven't seen it before, without doing a lot of advanced math, you're not going to know it. Believe it or not, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, the sum of 1 plus a 4th plus a 9th plus a 16th, and so on.
Is it pi over 6?
Close. Turns out it converges to pi squared over 6. That's right, believe it or not, this sum of, these nice looking fractions happens to converge to something with pi in it. A limit that is much less nice than the individual terms that we're adding up. Call the ambulance. We have ourselves a crazy series. So this is a famous example of this is what's called a Basel series. This series right here, it's a famous series that was studied by mathematicians for a while. Because for a long time, mathematicians knew that this series converged from the integral test. They didn't know what it converged to. Until finally Leonard Euler, not Euclid, Euler, came along and actually proved that this series has to converge to pi squared over 6. We're not going to prove that right now because it's a little bit difficult to do that. If we have time towards the end of the semester, we might look at a proof of why does this sum come out to pi squared over 6 of all things. But one point I want to make clear, the integral test can tell you that this series has to converge to something. It doesn't tell you what it converges to. It just tells you this series must converge to some number. What it converges to, you have to actually find out what it converges to by other means. Yes, James?
So the integral test, does it come from the same concept of how like the FTC is related to Riemann sums? It
is very much related, yes.
Okay.
So if you wanted to prove the integral test formally, what you would essentially do is you would take your infinite series, write it as a Riemann sum, as one of these limit as n goes to infinity, sum from 1 to n of blah, and do a bunch of messing around.
Okay.
It gets into a lot of messy details, which is why we're not going to
Yeah.
prove that in class, but that would be the essential idea of how it's related. Question? So, remember how we said take an integral of the form 1 over x to the n, and we call that a p integral? Time to talk about the p series really briefly. I promise you this will only take a minute, and I'll let you get antsy. You're getting giggly. Or I'm in Stevie, you're having a field day back here.
Not personal, it's just like tornado watch behind me, or notification. Shouldn't even be.
We just got a tornado?
Tornado warning.
That's a tornado
That's
warning.
when the siren went off.
Oh, hey, you know what? I think that's a good place to end on then. Alright, there's severe weather in the area. Stay safe. You might want to stay indoors for a bit. I don't know. Master Econometrics professor. I'm sorry, it's hard to pay attention to what's going on outside when you're teaching class. Okay. Stay alive.
Yeah, but my high school's on spring break right now.
Oh my god.
Yeah.
You guys class and like
Yeah.
I've never ever been
Alright, send me an email to remind me, but that should be fine.
Okay.
Stay at 11 tomorrow at 1?
Yeah, that's
Sounds
Yeah,
good.
we'll do it today, but.
Yeah.
Yeah.
Oh yeah, this is even near school, so.
Do you think I should drive home right now, or? Yeah.
I think right now it's just a watch, so you're probably okay.
Okay.
I'm gonna keep an eye on the roads and such though.
Yeah, I'll just start
Yeah, I was gonna say, if it takes us to a warning, then get indoors quick.
Okay. Alright, see ya.
Yeah, take care.
Never lived.
In a spot where tornadoes happen, in rural areas of Connecticut, they just don't.
Oh, yeah, I grew up in Kentucky, you get them quite a bit.
Oh, that's right. Have a good day,
Thank you, and thank you,
Oh, just one more
and
question.
thank you.
Just one more question about this. So we only care if it's not gold, so we just compare these two and this I agree with this. If we get the limit, it would split the new
Yeah. Yeah, because typically when we're taking the series is defined to be the limit of the partial sums, not the individual terms themselves. So in this case, the individual terms, the 1 over square root of n's, are going to 0,
Right.
but as n goes to infinity, the partial sums, and thus the series as a whole, are going to infinity because it's greater than a single thing going to infinity.
Yeah, if we just add up all these terms, it would. Yeah, good.
Even if the individual terms themselves at the end are going to 0.
Oh, okay, makes sense.
That's basically like 1 over square root of n plus 1 over square root of n.
This sum right here?
No, this one, like this one.
Yeah, because, in fact, that's exactly the same as adding 1 over square root of n to itself n times.
So yeah, we're adding this to itself over and over again, and that's why this would be bigger, right?
Well, we're not adding this to itself over and over again. The comparison that we made is that this sum right here is greater than what we would get if we added 1 over square root of n by itself over and over again.
So like 1 is greater than 1 over the square root of infinity. Because the square 1 over the square root of infinity goes to 0, and like this and this are both greater than that, so yeah.
Yeah, so we're not adding this to itself, we're just taking the limit as n goes to infinity of this sum. But this sum by itself is always going to be greater than the corresponding sum of just 1 over square root of n, however many times you have. And then it turns out that since this sum shoots off towards infinity, this sum which is greater than it is also going to shoot off towards infinity.
Okay, we just added it's just some value that's greater than the.
Yes, because we're assuming n is greater than 1, 2, and everything before it, and
Okay,
how we write this out.
okay, I think that makes sense. Yeah, okay.
Groovy.
Yes, then convergence, then according to the convergence test, with that.
Divergence test, what is that?
Okay. But the one.
Could you mean the divergence test?
The divergence test would be better, yeah, I agree. So, okay. Yeah, so you, oh wait, yeah, we don't have class Friday, right?
Yeah, no, we don't have class now for a full week.
Alright, I still have class Friday for philosophy, it's kind of funny, it's just,
Yeah, yes, unfortunately, it's some cancel board, some don't, it's
Yeah.
sort of up to individual professors.
Yeah, well, appreciate it. Nice to have a little extra day.
Is it possible to come into your office hours later today at 11 for your test? Awesome.
Yeah, sounds good, send me an email, but that should be fine.
Okay.
Have a good day, Dr. Crystal.
Yeah, you too.
What class is this? My sister's?
I would say your sister's, except your sister hasn't come to class for like 2 weeks, and apparently I'm not gonna see her for over another week, so
Interesting.
I don't know if I'd call it your sister's class anymore, but yes, it is Gov 2.
Why not Friday?
I've canceled class on Friday,
Oh, okay.
just like I've canceled class for you on Friday.
Thank you.
Yes, so you're supposed to get back tomorrow sometime, are you? Cool.
I think tomorrow evening or tomorrow night or something.
Okay.
Are we in the lab today? I don't know, maybe. Looks like it's-
Oh, I never ended the video.